Hi everyone, welcome to the video series on Essential Statistics, a primer on data science and machine learning. Focus will be on foundational concepts that form the basis of statistical reasoning and analysis that is required in the context of data science and machine learning. So whether you are starting as a data scientist or a machine learning enthusiast or a professional, looking to improve your data science skills or analytical skills in data science project, this primer aims to provide you with the necessary information in an organized manner in topic-wise format, essentially. From measures of central tendency to inferential statistics, we will cover fundamental topics that help you to structure your data science project. Video also addresses to bridge the gap between theory and practical applications, and I will try to give you as many real-world examples using Python, NumPy, Pandas, SciPy, and some of the plotting tools. So let's get started. So, as in terms of prerequisites, we need basic Python as a language skill, some elementary concepts on probabilities, and somewhat a little familiarity with data and data quality challenges. The topics that I have structured are the following. First, I'm going to talk about the context and overview. In this particular video, I'll especially talk about these two areas, why data science and mathematics is important in machine learning and deep learning. And then subsequently, I'll talk about the data types. After that, we will look into population and samples, and we'll try to correlate that with why we have to learn about population and samples for a typical data science project. Understanding centrality of the data is very, very crucial. So that's central measures. Dispersion is how the data is spread. So we'll talk about a couple of methods or even 4 or 5 methods how to measure dispersion in the data set or data series. After that, we'll get familiar with basic distribution, uniform distribution, and normal distribution to get started in this primer course. One more thing, this is just a primer course, and there will be an advanced video series as well. So in the advanced video series, we will talk about some other distributions like um, the other distributions like exponential distribution or the other distribution that we use in data science. We'll also talk about symmetry of data and why it is important to study the symmetry of the data series. Post that, the most important topic will be groups and relation, where we will talk about covariances and correlations and how is that understood from a geometrical perspective and in which field in data science, or what type of projects, we apply the ideas of groups and relations. So what you get at the end of this primer video series is essentially a end-to-end understanding of descriptive statistics, proficiency in calculating, interpreting the centrality or central measures, and be able to understand the data spread and understand the structure of the data column series and plan necessary actions in terms of removal, transformation, and further data engineering. So I'm going to be first starting with the overview on why statistics and mathematics is required, or they are the first step towards learning AI. So the data science actually is a wide, field where range of skills are required to perform a data science, activity as a project. So the level of probability and mathematics required can vary depending on the complexity of the project and the role that you're playing within the project. So typically, I have divided the data science role or data scientist role in three different buckets. Let's try and see what those buckets are. So level one, entry level data scientist, where you're focusing on basic data analysis and cleaning and visualization tasks. Very foundational understanding of probability and math is required. Really not required to go too deep into, let's say, linear algebra. We don't really need to go too deep into linear algebra, let's say, eigen decomposition and so on and so forth. So the topics level one data scientist will deal with is this descriptive statistics, probability basics like probability distributions, especially the normal distributions, a conditional probability understanding, hypothesis testing, and some histogram and scatter plot and a bar plot and a line plot. Those form the crux of exploration. A little bit of mathematics, understanding of vectors, and some idea about differentiation and the gradient, basic optimization techniques. So this is what the level one data scientist requires. And in all of these, we can see there is a fair amount of statistics and mathematics. As you go deeper into level two data scientist role, you are now talking about, let's say, Bayes theorem or Bayesian statistics, some advanced statistical inferences using ANOVA, and ANOVA has many other variants. Similarly, regression analysis starts with linear regression, but it can go really deep and it can be different forms of regression. Time series analysis is a very complicated statistical topic. Again, the mathematics, the level two data scientists might need to understand matrix and matrix decomposition, singular value decomposition, and many other decomposition methods. And those have extremely useful applications in data science. Optimization techniques, again, in the previous one also, I mentioned the basic optimization, but now here the optimizations would be slightly complicated. And then the data scientists at level two may need to understand information theory, the idea of entropy, and mutual information. So a deeper understanding of probability and mathematics is required at level two. Level three data scientist is advanced or scientist or research scientist sort of a role. Very strong mathematical foundation is required. Why now we are talking about Markovian statistics or Markovian methods to deal with uncertainties in the model, non-parametric statistics. Another area where things get a little complicated, as I mentioned, the time series analysis and the linear algebra. Also, we have the opportunity now to use singular value decomposition, some multivariate analysis, especially for data generation. And Kullback, Leibler divergence, just an example here. There are many other similar to Kullback divergence method where you comparing the distributions. So these are examples that I have listed. So we can appreciate the fact that knowledge of mathematics and statistics is indeed important. The level to amount of knowledge will vary from level to level. So specific requirements, and that's why the level of knowledge is or application of statistical knowledge and mathematics will vary. The more important will be practical experience and domain understanding, and tools like Python, R, and machine learning libraries are the key context for statistics and mathematics. So probability and statistics, where we actually use, I've listed a few examples here. So data science is all about estimating and predictions are nothing but probabilistic in nature. So let's look at an example here, sales forecasting. Here we are trying to forecast the sales for a particular region or a product or a group based on historical data. So this is all probabilistic measure. Another example here, financial modeling, predicting revenue or expenses or profitability. This again is based on historical data, but the outcome or predictions are all probabilistic in nature. Some more examples, sentiment analysis, for example, here, let's say we have a review comment by users and we want to know, is it, positive and negative. So there is nothing like deterministically positive and negative. It's all probabilistic. So a review comment, when it is fed into the model, is going to return you some probability. For example, let's say this is my review comment and the model says, positive is 0.41, 41%, and negative is 0.59 or 59%. So this is how typically things look like in all machine learning. Similarly for stock forecasting as well, so that is also probabilistic in nature. So the medical diagnostic, let's take an example, here of a rare disease, and here how do we make an assessment that the disease is present? Again, is a probability. So if that probability is beyond a threshold, then we say that disease is present, otherwise is not present. So likewise, weather forecasting is another example where you're predicting the likelihood of rain. So this is also probabilistic in nature. So it will return you two things. One, probability of rain. The other one is no non-probability uh, of raining. So whichever is higher, that's what we go ahead with. So statistical methods rely on probability. For example, hypothesis testing. We will be talking about hypothesis testing quite significantly in our advanced topics in statistics, not in the current primer video series. So, for example, the objective is to determine if the new drug is effective in lowering the blood pressure. So again, this is an application of probability here. Regression analysis is about, let's say we are trying to find out the relationship between hours of study and exam score. Is there a mapping? So again, the concept of probability is used here. So in all of these projects, the reliance on data is quite significant. And the process of data analysis is a very standard stage-wise. So you're going to inspect the data, clean the data, transform, and then prepare the data for modeling. After that, when we apply our statistical analysis or machine learning, we gather or extract useful information. And this involves various methods and techniques to extract the insights. And all of this is based on probability. So let's take an example here. So when you describe the data, it's about describing the data in terms of mean median mode, or it could be histogram or a box plot or some other visualizations. Sampling and inference is a very important topic. We will be covering sampling processes in this particular video, in this primer video series. So based on the sample, we will infer about population. That means, let's say we have some bunch of data length of certain measurements, and we have 100 samples. Based on the 100 samples, we would like to make an inference of what's the typical length generally for the population. So these are heavily dependent on probability. Predictive modeling based on machine learning, as I mentioned, this is predictions are all based on probability. So this topic of machine learning will be covered in the machine learning course. Hypothesis testing, I mentioned this a little while ago. This will be significantly dealt with in our advanced statistics. This topic will be covered in the statistical topic, like advanced topic. And anomaly detection is a fairly advanced application of machine learning. And here, similar to the rare disease detection, anomaly detection is actually a rare disease detection, or rare disease detection is an example of anomaly detection. And likewise, the typical bank transaction is a normal transaction, where anomalous would be which is non-typical, something in terms of high amount and all that. So anomalies are nothing but unusual events and errors, and the fraud and statistics and probability plays a significant role. So why we need to know about mathematics? So far we have been talking about statistics and probability. Why do we need to know about mathematics for data science and ML projects? The answer is here. Most of the algorithms are mathematical in nature. For example, decision trees, neural nets. So this is very then useful to really understand how the algorithms actually are designed, and that understanding helps us prepare our data or infer from the outcome of the models. Another useful phase in machine learning is feature engineering. A very heavy use of statistics and mathematics is used in feature engineering. For example, linear algebra methods, singular value decomposition, eigen decomposition, these are all examples of feature engineering. Optimization topic is based on differential calculus, or partial differentiation, or gradient optimization, and so on and so forth. So these are very crucial part of machine learning and deep learning. Validating results and evaluation of the model also requires a deep understanding of the measurement metrics, or the metrics for accuracy, precision, recall, and some of the advanced metric as well. Now, the new area where there is a lot of focus, which is the interpretability and explainability. Why the prediction came out the way it did, and that's heavily a mathematical subject. So understanding mathematics for explainability is very handy for data scientists. The tools that we will be using in this course is NumPy, SciPy, and some places I'll be using stats model as well. Stats model is slightly older version of statistical tool in Python. So that's pretty much it, and I hope we now appreciate the reasons why statistics and maths is important. In the next video, we will talk about the data types that are used, typically in statistics.